Hello everybody and welcome to the ROS Control 101 microcourse. First thing first, let's go to the Robotics Night Academy website. There it is. And select the course we are interested in. In this case, it is the ROS Control 101 course. So let's start this course. Great, and wait a few seconds until the system loads. There it is. So our system is fully loaded. We have the notebooks here in the left side, the IDE, the web shells, and finally the simulation window here. In this case, it has loaded a P-robot simulation, as you can see. So let's start with the course itself. This first chapter is a brief introduction to the course, some things you need to know, and a very quick demonstration to see more or less what you are going to do in the course. So first of all, what is ROS Control? ROS Control basically are a set of packages that allow you to control a robot. As the name says, ROS Control, that's the main purpose of ROS Control, is to make you control your robot. Now in this course we are going to focus in controlling a simulated robot. But the ROS Control packages also work with real robot, of course. Yes? So, what are you going to learn with this course? Basically, you are going to learn to see 3 points. One are some basic concepts about ROS Control, some basic things you need to know. Second thing is how to configure ROS Control to work with your robot simulation. We are going to also see how to do this. And finally, we are going to see how to create a custom controller, a very basic custom controller. All right? And how are you going to learn it? You are going to learn it by working in simulations. So by practicing, by doing exercises, by doing things is the way that we think you are going to learn better and faster. So in this course, we are going to work with the P-robot simulation a little bit. This one we have here. Also with an RR-bot simulation. And finally, you are going to do a project with the UR5 robot. So do you want to have a taste? Let's do a quick demonstration of what you can achieve with ROS Control. So let's execute the first command here, the first one in the demo. I will just copy and paste it here. Great. So with this command, what you're doing is basically to just load and start the controllers of the P-robot. Yes? Now, let's do a ROS Big List in another shell and grab by command, with the command word. Yes? So all these topics you are seeing here are the topics that have been launched where you can publish messages in order to control the different joints that are here in this case. Yes? So with these topics ended with command, you will be able to control the joints of your robot by publishing into these topics. And that's exactly what we are going to do in the third step of this demo. So let's, for instance, copy this command here and paste it. So as you can see here, what we are doing basically is to publish into this topic here, the Pi-robot head tilt joint position controller / command, and we are publishing in this case a 0. So let's see what happens here. If we execute this command, there it is. So as you can see, the head has moved. Yes, it has gone to its initial position, yeah? Great. So you have seen that you can communicate with your robot by publishing into these topics, right? Okay, let's try the second, for instance, which we are going to publish in a different joint, in this case in a different topic, which is the head pan joint position controller. Yes, so let's execute this command here. And as you can see as well, the head has rotated a little bit. Yes? Okay. So you are able to do this thanks to the ROS control packages. And in the course you are going to see how you can configure and how you can create a control package in order to control a simulated robot. Yes? Perfect. So we are done with the demo at this point. Let's stop everything. There it is. And here as well. Perfect. So for this course, you should have some required knowledge, yes, which is some basic ROS knowledge. You can get it, for instance, by doing the ROS in 5 days course in the Robotic Night Academy. It's one of the courses that we provide. So you need to have some basic ROS knowledge, some basic Unix shell knowledge as well, in order to be able to work well with the shells, yes. Also some basic joints knowledge, more or less know what a joint is, how it works, etc. And finally some basic URDF knowledge. All of this is very basic knowledge, yes. You don't need to be a pro in URDFs, for instance, but just be familiar with these topics, right? Perfect. And finally, I want to give some special thanks to Adolfo Rodriguez, which is the person that has created these ROS control packages and which maintains it. Here you can check his personal repository, also the ROS control wiki page. And finally, as well, to the Gazebo community, of course, for working in the integration between ROS control and Gazebo. So let's start with the course itself, with the real core of the course. So for that, let's click here in the next button, which will take us to the second unit, to the next unit. There it is. So now, some basic concepts. First of all, what is ROS control? As I've previously said, the ROS controller are a set of packages which include, for instance, here you have the controller interfaces, controller managers, transmissions, hardware interfaces, and control toolbox. And all these packages allow you to basically control your robot. Yes, to control the different joints, to be able to move them, to communicate with them, etc. So a very brief explanation of how the ROS control packages work, as kind of summary, is that the ROS control packages take as input the current joint state data, so how the joint is at that moment, and a set point, a set position, a goal to achieve by that joint. So where do you want to move that joint, for instance? Yeah. So it takes these two things as an input, the joint state and a goal for the joint, and it processes this data, and at the end it gives as an output the appropriate command in order to achieve that goal, in order to achieve that set point. Yes? Usually this is done by using a generic control loop feedback mechanism, which typically is a PID controller. Okay, but that's too much data. I think that the big picture you have to get is that basically the ROS control packages allow you to control your robot, and they take a goal position, a goal point, a set point as an input, and as an output they provide the required command in order to achieve that goal. All right. So here, for instance, if you make this bigger, here we have a diagram of more or less a brief diagram of how ROS Control works. So here we have the third-party apps, which in this case they appear navigation, move it. These ones would be the ones that are providing the goal, which is the desired goal position for the joint, for instance. Yes? So for move it, the navigation stack can provide a goal to the ROS control packages. And then the ROS control packages will give us an output to either the real robot, which would be this one, or the simulated robot. The ROS control packages will provide the command in order to achieve that given goal. Yes? And inside the ROS control packages, we are going to see a little bit what happens. So basically, we are going to focus now from the ROS control packages in two things. One is the ROS controllers, yes, which would be this part here. Yes, so the ROS controllers. There are many ROS controllers, but for this course we are going to focus in the most typical ones, which are the effort controllers, position controllers, velocity controllers, and joint state controllers. Yes? Then each one of these ones, inside, it has a controller. Yes? And this may be a little bit confusing. Right? Okay, so as I've said before, in the ROS control, you have an input and you have an output. Yes? So, for instance, here we have the ROS controllers, and this will get as an input a goal, which will come from anywhere, yes? They will get an input value, and they will provide an output value, yes? So in this case, these effort controllers, position controllers, velocity controllers will be the output value. So, for instance, if the joint that you want to control, it is an effort joint, it is a joint that works with effort values, you will use an effort controller. Yes? Because the output of your controller will be an effort command. And if your joint is an effort joint, you want your joint to receive effort commands. So you would use the effort controllers, right? If your joint works with position values, then of course you would use the position controllers, because you will want your joint to receive position values, position commands, right? Then these values you see here are the type of inputs that these controllers receive. So for instance, the effort controllers, which are used in order to control effort joints, can receive as an input, as a goal, can receive effort values, position values, or velocity values. Then you would ask, okay, but if I send a position value to that controller and it gives me in the output an effort value, what happens here? Well, basically inside the controller, these position values are transformed into effort values. Yes? But that is done internally in the controller. So we are not going to go that deep. Yeah? But basically you have to get this idea. So each controller has an output value and an input value. Yes? So if you work with an effort joint, you will be using, of course, the effort controller. But it will be up to you to configure which kind of input values you want to send to your controller. If you want to send effort values, position values, velocity values, whatever. In the position controller's case, for instance, or in the velocity controllers, the output commands are the same as the input commands. So if you use a position controller, you will only be able to send position values, and you will get at the output, of course, position values. Yes? And the same for the velocity controllers. Yes? So basically, you will use one controller or another depending on how the joints of your robot are built. So if your joint works with effort values, you will have to use the effort controllers, right? If your joint instead works with position values, you will have to use then the position controllers, right? The same for the velocity controllers, but these ones are less used. The most common are the effort controllers, the effort joints, and also a little bit the position controllers, yes? The velocity controllers are the less used. So, okay, and what happens with this one, the joint state controller? Why I haven't talked until now about this one? Okay, for this one, you will have to use it always. Yes, it doesn't have anything to do with how your joints are built, how your joints work. You will not have to choose between one or another like these ones. This you will have to use it always, because this controller what does basically is to provide continuously the state of your joints. Yes? And you will always want to know the state of your joints, how your joints are, if they move, update their state, etc. So with this controller, you will basically be providing the state of your joints at every moment. Yes? So this one is very, very important, the joint state controller. So basically, summarizing all this, depending on how your robot works, depending on how the joints of your robot work, you will use the effort controllers, the position controllers, or the velocity controllers. Yes? That's depending on the hardware, on how the robot, on how the joints work, which kind of joints they are. If they are effort joints, position joints, etc. And then you will always have to use the joint state controller, because with this controller you will always have access to the current state of your joints. All right, great. So let's do a very quick exercise, which is this one here, and it is to check which type of controller is the P robot using. Yes, and for that it's very easy. We can just follow this exercise here. So let's go to the package that contains the P robot simulation, which is this P robot package here. And then I'm going to execute this command here. Okay, so I'm basically copying a file into my workspace. You will see why I'm doing this. Okay, so I execute this command here, shown in the exercise, and the file will appear here. Yes? So let's open this file in the IDE, which is much more pleasant than visualizing it through the shell. And if you check this file, you will see that it's basically using, as I've said, the joint state controller. Yeah, this one you will always have to use it. So here you have it, in order to provide the state of the joints. And then it is using the effort controllers with an input of joint position controller. Yes? So in this case, all of the joints, you can see this one, but also this one and this one, they are using this type of controller. Yes? They are using effort controllers. So these controllers will provide effort commands, and as an input, they have a joint position controller. All right? Very easy, you see? This is just to let you interact a little bit with the system and to get familiar with the system and with the configuration files as well, since you will be creating yourself one in the next chapter. So what happens after the controller sends its output? It sends this output, this command directly to the robot? No. Before it goes through the hardware interface. What is the hardware interface? The hardware interface basically it is a software representation of the robot and its hardware. Yes, so it is a Yeah, software representation. And what does this do? Basically, in very brief, what the hardware interface does is to allocate each resource of the robot, of the simulation, for the controllers, and sends values to each resource. Yes. So basically, it is like a kind of intermediary between the controllers, between the controller plugins, and the real or simulated robot. Yes. As you can see here in the diagram we saw before, you have here the hardware interfaces represented, and as you can see, they act like a kind of intermediary, yes, between the controllers and the actual simulated or real robot. All right. And we basically have these two hardware interfaces. We are going to focus on these two. One is the joint command interfaces, yes, which are the interfaces that will send commands to the robot in order to perform the specific goal that has been set, yes. And of course, we have an effort joint interface to send commands to effort joints, a velocity joint interface in order to send commands to velocity joints, and a position joint interface in order to send commands to a position joint. And finally, of course, we have the joint state interfaces, which in this case will be, as we saw before, providing us information, constant information about the state of the joints, about the current state of the joints. Yes? Alright, so let's do this second exercise in order to see if we can detect what kind of hardware interface is the P-robot as well using. So, okay, we are going to copy this P-robot v2 WRDF file into our workspace as we did before. So I'm going to copy that file, which is, okay, it's P-robot. Okay, it is P-robot v2 URDF, and I'm going to copy it to my workspace. There it is. Let's wait. There we have it. Okay, so now if we open this file here and we go a little bit down, we are going to find a section which is right here, yes, where we have a transmission tag, yes, some transmission tag, we have 3 in this case, and inside these tags we see a hardware interface. Can you see it? Yes? We are going to see in the next chapter what these transmission tags are, a little bit more on how they work, yes? But from this, I can tell that the hardware interface that the P-robot is using is an effort joint interface. Yes? So it is this one here, the one that the P-robot is using. All right? So this one here. There it is. Great. Okay, I know it's quite maybe a little too much information and you may be a little bit confusing at this point, but don't worry. As you advance through the course, as you do the exercises, everything will start to make more sense. Yes? So let's not wait anymore and go to the next unit. So let's click again in the next button. And now you will see that the simulation will change. So we will not be working anymore with the P-robot. We are going to be working now with the bot. And there it is. Great. So as you can see, we have here the bot simulation. Perfect. So in this second chapter, we are going to see how to configure the controllers, how to configure the ROS control packages in order to work with the simulation, in order to control the joints of a simulation. How can we set up all this? Yes? So let's stop talking and let's go to work, which is the interesting thing and the thing you want to hear for sure. Okay, so the first thing we have to take into account when we want to integrate our simulated robot with the ROS control packages are the transmission tags. Yes? So we will need to add these transmission tags, if they are not there, to the URDF files. Yes? And what are these transmissions for? Well, basically, these transmission tags, what do is to describe the relationship between a joint and an actuator. Yes? This is a very brief explanation, but it describes this relationship between joint and actuator. Yes? And these transmission tags need to be defined in the URDF file. So, let's start with this exercise 2.1. Yes? So the first thing we are going to do is to check the URDF files of this simulation, of the airbot simulation, to see if they have or they haven't these transmission tags. So let's go to the simulation package. So you can see I'm just following these commands here. ROS airbot description, URDF, and I'm going to copy this airbot.chakra file to my workspace, as I did in the previous exercise. I'm going to repeat it. Great. So now let's open this file here. And if I hit Control F, I can find through the whole file any word. So I'm going to find the transmission tags to see if they are here or not. Okay, perfect. So in this case, as the simulation is already launched for you in the system, yes, so when you launched the unit, the simulation was already launched. In this case, you already have these transmission tags defined for this simulation. Yes, and as you can see, it uses as well an effort joint interface as the P-robot. All right, so for this case, we already have this information, these transmission tags, so we don't have to worry about this. If your URDF doesn't have these transmission tags, you will have to add them manually to the URDF. Yes? Okay, and let's have a look at how these transmission tags work. Yes? So basically you have these 4 tags to define inside the transmission tag. You have the type, the joint, and the actuator. The type will define the type of transmission that will be used between the joint and the actuator. In this case, the only transmission available is this one, the transmission interface / simple transmission. This is the only one you can use at the moment. Yes? So in this case, it's very, very easy. Yes? As you can see, the type is transmission interface, simple transmission. Yes, this is the one you have to use. This is the only one available. Great. So the second tag you will need to define is the joint tag. In this case, this tag will provide some information about the joint that is connected to this transmission. Yes? Basically, you will need to define 2 things. The name of the joint, which in this case it's joint 1. This is defined in the simulation itself. Yes, so when you create your simulation, you will give names to your joints. So when defining this transmission tag, you will have to specify the name of the joint, yes, related to this transmission, which is here. As you can see, in this case, it's the joint 1. And you will have to define a hardware interface, which will depend on how your simulation works. If it uses an effort joint, you will have to specify here the effort joint interface. Yes? So we have the type, which is the simple transmission always. Second, we have the joint tag. We will define the name of the joint, joint 1, and the hardware interface that it will use. Yes, the effort joint interface in this case. And finally, we have to also describe the actuator tag, which will contain, as well as the joint tag, the name of the actuator and the hardware interface. And also in this case, we have the mechanical reduction tag. This one is optional. You don't have to define it if you don't want to. But usually it is defined and it's set to 1, almost always. But as I said, this one is optional. The ones that are mandatory are the type tag, the joint with the name and the hardware interface, and the actuator with the name and the hardware interface. Yes? Perfect. So this is how you would define the transmission tags for your simulation. In this case, we already have defined it. We already have them defined, so we don't have to worry about them. But if you don't have them, you will have to add them. Great. Now the second thing we'll have to do is to add the ROS Control, the Gazebo ROS Control plugin, also to the URDF files. Yes? So once we have our transmission tags in the URDF, we have to add the Gazebo ROS Control plugin. Yes? And how would this be done? Okay, let's have a look. As well, let's follow this exercise 2.2. Let's copy this file, the airbot.gazebo to home, user, cutting workspace, SRC, to our workspace. There we have it, very easy. So here, at the top of the file, you will see these lines here. Here is where we are calling, where we are starting the Gazebo ROS Control plugin. Yes, and this is also mandatory. So as you can see in this file as well, we already have it, because we cannot modify the URDF files of this simulation because it is already launched. So in this case, we already have this plugin launched here, yes? But if you don't have it, you will have to add it, yes? Let's see more or less how you will do this. Okay, so basically, before explaining how to add it, basically what this plugin does is to read the information contained in the transmission tags we created previously, yes, and loads this information properly so that Gazebo, so that the simulation can understand them, yes? So it translates these transmission tags into information that Gazebo can understand, basically. Great. So how this works? Great. So when adding this plugin, you will have to always, mandatory, add this plugin tag here, which contains the name and the file name. All right. So let's have a look here in the IDE. So as you can see, we have, first of all, the Gazebo tag, of course, and then we have this plugin tag, yes? In here, we will define the name of the plugin, which is Gazebo ROS Control, and the file name where this plugin is, which is this one here, libgazebo_ROS_control.so. Yes, because it is a library, compiled library. So this is probably the most important line here, yes? This plugin line here, of course, here it is closing the tag, yes? But this tag here, this line here is the most important. and this is actually it's the only mandatory line in order to load the Gazebo ROS Control plugin. Yes? So always you want to add the ROS Control plugin, you will have to have the Gazebo tag with this plugin tag inside. Like this, Gazebo ROS Control and libgazebo roscontrol.so. Alright? Then, inside this plugin tag, we can have some other tags. We are going to have a quick look now. Okay, the first one is the robot namespace tag, which basically defines the namespace to be used by the instance of this plugin. Yes, and by default it will put the name of the robot that is defined in the URDF file. When you create the URDF file of your robot, you will put there a name for your robot, and by default, if you don't specify anything, it will use that name as the robot namespace. Yes, as you can see in this file we have it defined, and we are using this RRBot namespace. All right. Then second, we have a control period tag, which defines the period of the controller update. And by default, it uses the Gazebo period, and this tag usually is not set. Yes, it's very strange to have to set this tag. So as you can see, in this simulation, it is not defined. So we just have the robot namespace and the robot sim type. Yes. So this one is more strange. So let's move on. We also have this robot param, which as the control period usually is not set as well. Because by default it uses the robot description. By default it uses robot description. Yes, and in most of the cases this is the correct value to use the robot description. Yes, but if for some special case the location of the robot description parameter in your simulation is different, you can set it here in this robot param tag. Okay, and finally we have this robot sim type tag. And what does this tag define? So basically what this tag define is the plugin name of a custom robot hardware interface to be used. Yes? So it may happen that you want to use a custom hardware interface, but this is for more advanced users. Yes, because this is quite complex. So for a regular case, for a basic case, you will always use this default robot hardware sim. Yes, which is the one that we have defined here. Default robot hardware sim. Yes? And by default, so if you don't specify anything, it will take automatically this one. Yes? So putting this, in this case, is the same as if I remove this tag. Yes, because by default it will take this default robot hardware sim. Alright? So in most cases, when defining the Gazebo ROS Control plugin, you will just have to define the robot namespace and the robot sim type. But usually, as I've said, in the robot sim type for basic users, for not advanced users, you will be using the default robot hardware sim value. Alright, and why I say this? Because this default robot hardware sim, what does is to interactuate, it allows you to interactuate these interfaces, the joint state interface, the effort joint interface, the position joint interface, and the velocity joint interface. Yes, which are the basic ones, the ones that we saw in the basic concepts unit. You remember them? So by using this one, the default robot hardware sim, we'll be able to access to these interfaces, which are the most common ones. All right? Perfect. So let's move on. So once we have defined the transmission tags and we have added the Gazebo ROS Control plugin, Now we are ready to actually create the control package. Yes, the package that will allow us to control the joints of our simulated robot. So let's go for that. And that is what we are going to do in this exercise 2.3. Okay, so the first point I have is to create a new package, name it My Robot Control. And I will place inside a config and the launch folders. Great. So I'm going, oops, what I go here? All right, so I'm going to my source, and I'm going to name my robot control. Perfect. So I have created this package, which will appear in a moment here. There we have it. Okay, and inside this package, I'm going to create two additional folders, one called config and the other one called launch. Perfect. Okay, so the second step is to, inside the config folder, create the configuration YALM file. Yes, which I'm going to call it myrobotcontrol.yalm. So let's go for it. New file. And inside this file, I'm going to copy these contents here. So let's go for it. Okay. So what am I doing in this file? This YALM file, which is inside the config folder, what it's doing is basically to describe the controllers that I'm going to load, the controllers that I'm going to be using. Yes. So as you can see, we have the joint state controller. Yes, as always, joint state controller in order to get the state of the controllers. And then I am defining two more controllers for joint 1 and joint 2. All right. And what am I defining? So here I put the name of the controller, which will be joint 1 position controller. Then I define the type of controller that will be, which is an effort controller with joint position controller as input. Yes. Next, I define the name of the joint that this controller will control, which is the joint 1 in this case. And finally, I define some bit values. Yes. I am not going to get into bit values and how they work, but if you are working with a simulated robot, you should calculate yourself the bit values for your joints, all right? So I'm not going to go into this. So basically, in the YAML file, I define the controllers I'm going to use. Yes, I will put the joint state controllers as always, and in this case, I am defining two controllers. Yes, one for joint 1 and one for joint 2. And both controllers, as you can see, are effort controllers. All right, great. So our configuration file is done, and I think it's quite self-explanatory. It's quite easy to understand. Yes, so the next thing we are going to do is to create our launch file. So inside the launch directory, I'm going to create a new file, which I will call myrobotcontrol.launch, and I'm going to copy these contents into the launch file. Great. So now, what am I doing in this launch file? Basically, I'm doing three things. The first one here, as you can see, I'm loading into the parameter server my configuration file, the one I have just created here. Yes? So I'm loading this configuration file into the parameter server. Yes? This is what I'm doing in this line here. Next, what I'm doing here? What I'm doing here is basically to spawn the joint controllers. So I'm using the spawner function of the controller manager in order to spawn, to launch, to start my controllers, which are the joint 1 position controller, joint 2 position controller, and joint state controller. Yes? The controllers that I have defined in my configuration file. So here I am launching them. I am spawning them. Yes? And finally, what I'm doing here, what I'm doing is to launch a robot state publisher node that basically listens to the joint states topic, which is the topic where the joint state controller publishes the state of the joint. So this robot state publisher node is listening to this joint states topic, and it's publishing the information to the TF topic. And this allows us to for instance, visualize the simulation in RVs and do other stuff. Yes? But basically it's doing that. It's monitoring the joint states topic, so it's monitoring the state of the joints and publishes this information to the TF topic. Yes, so this is what I'm doing here in this third section of the launch file. All right, perfect. So let's go on. Yeah, here in the notebooks you have explanations, more detailed explanations of everything. Yes, I'm just doing a workaround and going fast in order to see some things. Yes, but here in the notebooks you will have explanation of everything. Alright, so what I'm going to do now is to launch my control package. Yes? So I'm going to do a ROS launch of my robot control package, which is this one, and my robot control launch. Yes? Which is the launch file I have just created. So let's launch this. Excellent. So as you can see, everything went fine, and it has started the controllers: joint 1 position controller, joint 2 position controller, and joint state controller. Excellent. So now, if I come to another shell and I do a ROS topic list, I will see that some topics have appeared. Yes? Specifically, these topics here have appeared. These ones have been launched by our launch file. Yes, have been started by our launch file. And here I have the topics related to the joint 1. As you can see, the command, bit parameters, and the state. The same for the joint 2, command, bit parameters, and the state. And finally, I have this RRBot joint states topic, which, as I've said before, this topic is the one created by the joint state controller. So inside this topic, the joint state controller will be continuously publishing the state of the joints. Yes? And we also know these command topics here. Yes? So with this RRBot joint 1 position controller command topic, I will be able to send commands to the joint in order to move it, in order to control it, all right? And the same for the command topic of the joint 2. All right? Perfect. So now let's test it. Don't you think so? Let's test that this works okay. And we are going to do it by publishing into those command topics. So here I'm going to publish into the command topic of the joint 1 position controller. Yes? I'm going to publish a message, in this case 1.5. So let's execute this command and see what happens. Excellent. Perfect. As you can see, the joint 1 has moved, joint 1, which is this one, has moved to the position 1.5 in this case, yeah? But has executed this command. So our control package is working perfectly. Yes? Now let's try this second command in order to move the joint 2. So, and there we have it. So the second joint is also being controlled by our controllers. So everything works okay. Yes? So you have created a control package for controlling this simulation. All right? So you already know how to create a control package for controlling the joints of a simulation, of a simulated robot. All right? Great. Okay, so now let's do a quick workaround of what else you can learn by doing this course, because if not, this video would be too long. And I think we have already seen some important things, some interesting things. Okay, so the next thing you will learn if you do the course, is to interact with the joints in a graphical way. So until now, you have interacted with the joints by publishing messages into the command topic, all right? Just by publishing messages into a topic. So in the next section of this notebook, of this chapter, you are going to see how you can interact in a graphical way. Yes? Specifically using RQT GUI, which is very interesting. Because you can do many things, you can visualize how your joints are performing in a plot, you can use the dynamic reconfigure tool in order to tune the pins. All of this you will learn how to do it here. Yes? In this exercise. Oh, there it is. So here you are moving the robot using a sine wave, a sinusoidal wave, which is also quite interesting. It's continuously moving. Yes, here you are also plotting the states of the joint. Yes. And here you will be tuning some of the pit values in order to improve the performance of your robot. Yes? Excellent. And this will end this chapter. So before moving to the next chapter, I am going to stop this. Excellent. So let's go to the next unit to see what you will be doing here. All right. So in this chapter 3, you are going to see how to create a custom controller. So until now, you have been using controllers that already are provided by the ROS Control packages, yes? The joint state controller, the effort, position, and velocity controllers are already provided. But here you are going to create a controller yourself, yes? Which is also very interesting. So this is what you are going to learn to do in this chapter 3, yes? As you can see, it has many steps. Create the package, create the source code, which is in C++, create a plugin description file, update the package XML file, update the CMake list, build the controller, write the configuration file, create the launch file, and test it. Yes, and with this controller you will be able to control the joints of your robot as well. Yes, this is very interesting as well. So let's move to the next chapter, which is the last one, and it is the project. So at the end of this ROS Control micro course, you will have a project to test everything you have learned. And this project will be done, as you can see, in a UR5 simulation, so in a completely different simulation. In this case, this is a robotic arm, yes? So the project will be done with this simulation. And you are going to do some steps that you have learned how to do during the course. So this is just to test that you have learned and understood everything correctly, yes? And this project has 4 steps, basically. The first one is to examine the simulation, examine this simulation because you don't know it, so check some important files and some information that you may need in order to complete the project. Second is to build the control package, as you saw in chapter 2, as we did together, is to build a control package for this simulation, for the UR5 simulation. Third step is to test the package, test that everything works okay. You can control, you can move the joints by using your control package. And finally is to create a controller, create a custom controller as well for this robot, for this simulation. All right? And that's all for this course. So we have done some exercises, some parts of the course together, but some of them I leave them to do it by yourselves, because this is the way you will learn more, by doing the things by yourself and having errors and struggling with the problems you find. Yes? So last of all, I want to remind you that if you finish this course, but you want to keep learning ROS, or you want to keep working with ROS control packages, keep testing your knowledge, you can go to the ROS Development Studio. Where you have many public simulations available, where you can, for instance, work with an airy worm, with a shadow hand. You have many public simulations where you can test your ROS knowledge. And you have also some private, in this case I have many, but if you are new to RDS you will have this section empty. Here you can create simulations from scratch, you can choose the simulator you want to use, Robotics, Gazebo. You can create your own simulation from scratch and work with ROS and keep testing your knowledge and do whatever you want. And as well, if you want to keep learning and do other courses and learn about other things, you of course have the Robot Ignite Academy, where you have many courses, very, very interesting. For instance, I have here the ROS in 5 days, which is the basic course. If you don't know nothing about ROS, you would come here. ROS Navigation in 5 days, which is also very, very complete and very interesting. ROS Autonomous Vehicles, TF Transforms in ROS, EarthTab Map, which is building a 3D map in ROS, OpenAI Gym for robotics, ROS Industrial, whatever. And the platform will be continuously being updated with new and new and new courses. So don't doubt it and come here to learn ROS. And that's all. I hope you have enjoyed this video and I hope to see you soon in any other ROS tutorial. Goodbye.